My name is Kevin Tierney and I'm a professor at Bielefeld University in Germany. Today, I'm going to tell you about how to more effectively solve combinatorial optimization problems using reinforcement learning. More specifically, I'm going to tell you about efficient active search for combinatorial optimization problems, which is a problem-independent method for searching for high-quality solutions using a learned model. This is joint work with my PhD student Andre Hotong and with Youngdae Kwon at Samsung SDS in South Korea. Thank you to both of them for their great work on this project. Developing algorithms for new problems is time-consuming and requires significant operations research and problem domain expertise. Wouldn't it be nice if we could just learn how to solve an optimization problem given a description of the problem and a set of representative instances? There are a number of advantages of being able to just learn an algorithm in this way. First, it lowers the barrier of entry to solve OR problems, essentially turning them into data science problems. This would allow organizations to solve OR problems that currently lack the expertise to develop optimization approaches themselves. Second, the heuristic would be customized to the problem instances. The algorithm configuration community has shown repeatedly that adjusting algorithm parameters to a dataset is critical to achieving the best performance. So if we learn an algorithm for a dataset, we can directly target specific instance classes. Third, reinforcement learning, when using deep neural networks, can exploit the GPU for optimization purposes, opening up a mostly unused avenue for combinatorial optimization. Of course, there are some downsides of replacing handcrafted heuristics with learned ones. The first is that the learning phase is computationally expensive and requires at least one GPU. Furthermore, the algorithmic interpretability is likely lower than for handcrafted solutions. In other words, the learned model will make decisions about how the solution should look, but we have really no idea why. This stands in contrast to human-designed algorithms that usually have some kind of explainable heuristics guiding the solution process. Before we look at what is new in this work, let's examine how reinforcement learning for combinatorial optimization problems works. We generally consider a solution construction process in which the solution starts empty and components are iteratively added to the solution. For example, in the case of the grasp metaheuristic. The key to this field of research is that instead of deciding what to add to the solution based on a heuristic, we query a learned model, such as a deep neural network, and receive a probability distribution over the potential actions available. We select an action according to the probability distribution, perhaps the argmax, or by sampling the distribution. Consider building a solution to the capacitated vehicle routing problem. We start with an empty solution, 3 vehicles each with capacity 10, and a set of nodes to visit, each with an amount of demand. We query the model to find out where to send the first vehicle. We'll use an argmax strategy here and select the node with the highest probability as assigned by the model as shown. The model is queried again, and the node with the highest probability is again chosen. Note that infeasible nodes are masked, meaning we do not allow the solution to become infeasible. In this case, the only choice is to return to the depot, since the vehicle is carrying 9 units of demand. This process continues until all nodes are serviced by a vehicle. The goal of our work is to improve the ability of these models to find high-quality solutions. The 2 main ways of doing this right now are using sampling and beam search to examine more solutions than just the greedy one. In this work, we show how an efficient active search strategy involving backpropagating information about the solutions we find while searching can significantly improve the performance of RL methods. Bello et al. 2016 proposed the idea of active search, in which the weights of a trained model are adjusted with respect to a single instance at test time using reinforcement learning. For clarity, the process of using an RL technique for combinatorial optimization looks like this. In the training phase, which is performed offline, training instances are used to train a model using a standard RL technique, such as the policy gradient or actor-critic learning. Once the model is trained, it can be used to solve previously unseen instances. Given a test instance, the trained model is queried as seen before to provide a solution. This solution can then be used to adjust the weights of the model to generate new solutions. This results in the model generating better solutions in subsequent iterations. The disadvantage of this approach is that active search changes all of the weights of the model, which is rather computationally expensive. The research question that arises is thus whether we can make active search more efficient so that we can examine more solutions in less time. Consider this graphical overview of an RL algorithm solving a combinatorial optimization problem. It's basically the same as before, with a bit of extra detail added, namely the encoder and decoder. The encoder accepts the instance and creates an embedding. In the case of the TSP and CVRP, the encoder generates an instance representation out of n-dimensional vectors that represent each node. The decoder then translates the representation into an action. The key question is, do we really need to adjust all of the encoder and decoder weights during the active search phase of the algorithm? The answer is no, and we evaluate 3 different strategies in this work that only change a small subset of the model parameters. Note that our proposed strategies still allow the model to perform batch instance solving, thus retaining a key advantage of the GPU. The first strategy is to add an extra layer in the decoder in the active search phase and only update the parameters of that layer according to the solution seen. The obvious advantage is that updating only the parameters of this one layer will be significantly faster than updating the whole model. A disadvantage is that the gradients must be computed all the way up to the new layer, so the closer the layer is to the output layer, the better. The question, of course, is whether just updating one layer is enough to still provide search guidance. Here's a spoiler for you. It is! An alternative strategy is to just adjust the embeddings generated by the encoder. As in the first strategy, this has the advantage of only requiring updates to a few model parameters rather than all of them. However, it can be updated without computing gradients for other parts of the network. Finally, the third strategy we propose does not rely on updating gradients. Instead, we maintain a table Q that is used to modify the policy. Q is updated based on the quality of the solutions previously seen that use an action AT. The idea is essentially the same as how ant colony optimization constructs solutions, except that the initial solutions are guided by the model rather than being random. We now evaluate the 3 different strategies on 3 different optimization problems. For the traveling salesperson problem and capacitated vehicle routing problem, we extend the POMO approach from Kwan et al. With EAS techniques. For the job shop scheduling problem, we extend the L2D method from Zhang et al. The main point here is that EAS can be applied fairly easily to any autoregressive model. In all of the following experiments, we report results on separate, out-of-sample test sets. This data is different than the data used to train the models. We refer to the test set as data drawn from the same underlying distribution, and generalization sets as those that are drawn from similar but not exactly the same distributions. Our goal is to evaluate how well EAS performs on the data it was trained on, as well as when the instances it is solving are slightly different from the ones it was trained on. On the TSP, we use a dataset of randomly generated instances. It is probably not that real world, but neither is the TSP, so it still provides an interesting benchmark. We train the models on n=100 sized instances and test them on a separate test set. Furthermore, we examine how well the models generalize to larger instances of size n=125, 150, and 200. Let's first examine the different algorithms being compared here. Concord is, of course, the well-known exact solver for TSP. Its performance is extremely good and practically unbeatable by any learned approach. LKH3 is the well-known Lin-Kernighan-Hellsgauen heuristic, which also provides extremely good performance on the TSP. The next block of algorithms are learned approaches from the literature. GCNBS is a graph-based approach, 2opt-DL an approach based on the 2opt heuristic, and LIH a construction-based approach. CVE-opt is an autocoder method that Andre Hotong and I developed that is also being presented here at Informs. Finally, DPDP is a dynamic programming-based approach that is particularly well-suited to the TSP. Note that we lack generalization results for most of these approaches as we do not have their source code. Next, we move into the POMO block of algorithms. POMO Greedy provides a baseline for our contributions and is the standard POMO approach. Sampling is POMO with a sampling mechanism on top of the greedy mechanism that improves its performance somewhat. Active search modifies all parameters of the model during test time, as previously discussed. This provides another literature baseline for comparison. Up next are our 3 EAS techniques. Here, EAS EMB stands for embedding, EAS lay for layer, and EAS tab for tabular updates. EAS techniques clearly outperform not using EAS on the POMO model and are rather effective at generalization. Normally, we would expect a learned approach to perform worse as the instances become different from the training set. We see this for both greedy and sampling. However, for active search and EAS, the performance only becomes marginally worse. EAS is thus able to counteract drift in datasets effectively. Of course, our recommendation would be that if you see your underlying data is changing, you ought to train a new model, so while generalization performance is nice to have, it's really not critical to the success of a method in practice. Note also the huge difference in solving time between active search and EAS. The DPDP approach is the best machine-learned method, at least on the n equals 100 sized instances, but we do not have generalization results for it available. The reason for DPDP's good performance is that it only calls its learned model a single time, and then initiates a dynamic programming procedure. This is well suited to the TSP, in which testing lots of different solutions quickly works very well. Most of the learned approaches, in contrast, query their models at each step of the construction process, which slows them down. Standard techniques like Concord and LKH3 outperform all RL techniques, probably due to the simplicity of the TSP. Simply put, most RL techniques are probably too expensive for this kind of problem. Who knows if we will ever match the performance of something like Concord? On the CVRP, the set of algorithms we compare to is slightly different, and we remove Concord as the CVRP is too hard to solve to optimality with 100 customers. First, notice that EAS techniques all outperform LKH3 by a fairly large margin for this instance set, both in terms of solution quality and runtime. The takeaway from this is that as soon as the problem starts to include some side constraints, learned methods have a chance against their handcrafted counterparts. EAS methods also outperform the state-of-the-art learned approaches. I would like to note that while DPDP achieves a very good score, it does use more domain information than the EAS approach with POMO, so the performance of EAS is especially impressive here, as it is domain independent. In terms of generalization, we see similar performance to the TSP. Without EAS, the performance of POMO rapidly declines as the problems become larger. But with EAS, we only observe a minor reduction in solution quality. We also evaluated a more real-world dataset for the CVRP. Each row in this table represents a separate instance set generated from Uchoa et al. 2017. We train a model for each instance set and test it. Here we see that EAS again significantly outperforms standard POMO even with similar runtime. Furthermore, EAS also outperforms the LKH3 heuristic by a reasonable margin, indicating that learned methods can indeed be competitive with handcrafted heuristics as long as the problem includes at least a side constraint or two. More details are available in our paper in the archive. Finally, we also test our approach on a rather different problem, namely the job shop scheduling problem. Despite the vastly different structure of the JSSP to the previous two routing problems, EAS nonetheless improves performance over not using EAS. Note that the L2D method uses dynamic embeddings, thus EAS does not have much of a time savings over active search. A question for future work is whether static embeddings plus EAS can outperform the information gain from dynamic embeddings, since static embeddings can search significantly more solutions. Interestingly, while modifying the embeddings works best on the JSSP, we generally saw the extra layer working better on the CVRP and TSP. Currently, we have no explanation for when modifying the embeddings or adding an extra layer works best, and encourage testing out the different possibilities on new problems. Since this doesn't require retraining the model, this kind of hyperparameter configuration is fairly cheap to evaluate on a validation set. In conclusion, we evaluated 3 different efficient active search strategies that can be easily added to a wide variety of RL approaches to combinatorial optimization problems. On the CVRP and JSSP, efficient active search significantly outperformed all existing RL-based methods. Finally, all 3 strategies significantly improve generalization performance. Please take a look at our paper in the archive. We also note that our efficient active search approach won the AI for TSP competition, which involved a stochastic orienteering problem with time windows. This independent test of the quality of efficient active search further shows the effectiveness of the approach. Thanks to Finn Schmidt-Olms and Meinolf Selman for their work on the competition, and thank you for watching this video.